Hello viewers, welcome back to the course on matrix computation and its application. So, today we are going to discuss a very important topic, that is Jordan-Canonical Form. So, let us start with that. Now, suppose I have a matrix A that is of order n cross n. So, it is a square matrix basically. And then we can find out its eigenvalue and eigenvectors. So, I can define its characteristic equation. So, I can define the characteristic equation. So, that is represented by taking the A minus lambda I determinant equal to 0. So, that is the characteristic equation, and suppose its characteristic equation is, I just tried, it is a polynomial. So, it is n cross n, I will get the nth degree polynomial. So, suppose I get the characteristics equation as, maybe I write just lambda minus lambda 1, maybe 4, lambda minus lambda 2, 5, and lambda minus lambda 3, maybe I just write n minus 9, because if it is nth degree. So, suppose this is my n cross n matrix, and this is the corresponding characteristics polynomial. And now root of this, so this is my characteristics polynomial, and if I put equal to 0, then I get the roots. Lambda I will get lambda 1, lambda 1, lambda 1, lambda 1, and then it is 5 times, it is 4 times, and the remaining is lambda 3, and so it is suppose n minus 9 times. So, in this case I will say that so these are the eigenvalues. So, I can say that the eigenvalue lambda is equal to lambda 1 has algebraic multiplicity has algebraic multiplicity 4, because it is 4 times it is repeating. Or in the short form I can write that algebraic multiplicity, just for the short form, for lambda 1 is 4. Similarly, I can write down the algebraic multiplicity of lambda 2 is 5, and algebraic multiplicity of lambda 3 is n minus 9. So, this is, we can write the algebraic multiplicity. Now, I want to find its eigenvectors. So, now to find eigenvectors, so what I need to do is that, so let us find the eigenvectors. So, first I take for lambda is equal to lambda 1. So, what I need to do is that I will take matrix A, and then I need to find eigenvector x corresponding to lambda 1. I should write x1. Okay. So, and x1 is not 0, that we already know. So, basically I need to solve A minus lambda 1 I x1 equal to 0, and from here I can say that I need to find out the value of this solution. It means I need to find the x1 that belongs to the null space of A minus lambda 1 I, or I can also write kernel of A minus lambda 1 I. Now, suppose the dimension of null space corresponding to the eigenvalue lambda 1 is 4. Suppose I have this 4, its dimension is 4, then I say that geometric multiplicity of lambda is equal to lambda 1 is 4. So, it means that the geometric multiplicity of eigenvalue lambda 1 is equal to the dimension of the null space of A minus lambda 1 I. So, now here I can see that the algebraic multiplicity of lambda 1 is 4, and I also assume that its geometrical multiplicity is also 4. We also assume that geometric multiplicity of lambda 2 is coming same as the algebraic multiplicity, that is 5, and geometric multiplicity of lambda 3 is also coming same as n minus 9. Now, from here you see that the algebraic multiplicity of the eigenvalue is same as the geometric multiplicity of the eigenvalues. So, in this form, in this case, we say that the matrix A is diagonalizable. And how it is diagonalizable? So, I can define the matrix P made up of eigenvectors. So, corresponding to the lambda 1 we have geometric multiplicity 4. So, suppose that corresponding to lambda 1 I will get for eigenvectors, they are linearly independent. So, suppose I have, maybe I just write here, maybe I can write x1, x2, x3, x4, and then I can write corresponding to lambda 2, I can write y1, y2, y3, y4, y5, and then corresponding to z1, z2 like this one. So, this is my matrix P, and all the column vectors are linearly independent. So, I can define its P inverse, and from there I can define my AP will be equal to PD, and I can write my PT P inverse, where D is my diagonal matrix, which is having the eigenvalue at the diagonals. So, lambda 1, lambda 1, lambda 1, lambda 1, sorry, lambda 1, then lambda 2 like this one, and all other elements are 0. So, this way it's, I can say that my matrix A is diagonalizable. Now, so up to here it is okay. Now, I see another thing, I will see that what will happen if matrix A is symmetric. So, in this case, suppose I have the matrix symmetric, that is I have A transpose equal to A. So, what is going to happen in this case, that when our matrix A is a symmetric matrix, then the things will change here. Now, we know that that symmetric matrix, I am talking about symmetric. When I say symmetric means it is a real, because otherwise it will become the Hermitian matrix when it is a complex. So, I am talking about the real matrix. So, I am talking about the real symmetric matrix has all eigenvalues real. That we have already proved in my earlier videos, that symmetric matrix has all the eigenvalues that are real. Also, I can show that also we can show that eigenvectors corresponding to different eigenvalues are orthogonal. So, that we can show. So, how we can show that? So, let us do this one, that I have A transpose equal to A, that is my matrix, and let lambda 1 and lambda 2 are the eigenvalues. Okay. So, then corresponding I have, suppose let V1 and V2 are corresponding eigenvectors. So, that I am able to find. Now, I want to show, so it means that V1 I have, so it means that A V1 is equal to lambda 1 V1 and A V2 is equal to lambda 2 V2, and of course, my V1 is not 0 and V2 is not 0. Now, so let us suppose I take what is lambda 1 V1. So, I just take this one, I write lambda 1 V1 taking the dot product with V2, this one I want to. So, I can define this one as lambda 1 V1 transpose V2, that is that thing we know. Now, lambda 1 V1 is A V1. So, I can define here it is equal to A V1 transpose V2. From here I can write this as A V1 transpose A transpose V2. Now, I can write V1 transpose A transpose V2, I can write like this one. Now, A transpose is equal to A. So, I can write V transpose, and this one I can write as A V2, this is V1 transpose, and A V2 is lambda 2 V2, and from here I can write this as a lambda 2 V1 transpose V2, because this lambda 1 and lambda 2 are real. So, no problem, and from here, and this is also I can write as lambda 1 V1 transpose V2. So, from here I can write that lambda 1 V1 dot product V2 is equal to lambda 2 V1 dot product V2, which implies that lambda 1 minus lambda 2 dot product V1 V2 is 0. Now, lambda 1 is not equal to lambda 2. So, that implies that my V1 dot V2 is 0. So, that shows that V1 is orthogonal to V2. It means for a symmetric matrix, for a different eigenvalue, the corresponding eigenvectors are orthogonal to each other. So, from here I can say that in that case we can write A as P D P transpose, because instead of, now what I do, I write a matrix P made up of eigenvectors, and that eigenvectors is orthogonal to each other. So, in that case I will get my P inverse is equal to P transpose, and the matrix P is orthogonal matrix. So, from here you can see that now this matrix A is diagonalizable, and in this the corresponding matrix P will be orthogonal. So, from here I can write like this one. In this case also let we have a matrix B which can be written as some P D P transpose. Let us write this one. Then I just want to check what is B transpose. So, it will be P D P transpose, and that is equal to P transpose D transpose P transpose, where D is the diagonal matrix and P is an orthogonal matrix. Let us write. So, from here I can write P and D is a diagonal matrix, so transpose is same, and this will be P transpose, and you see from here that is equal to B. So, which implies that B is a symmetric matrix. So, now from here I can write one important observation or a theorem, that N or I can write a matrix A square matrix is orthogonally diagonalizable if and only if A is a symmetric matrix. It means if A is a symmetric matrix, then we already know that this is diagonalizable, orthogonally diagonalizable, and here we have seen that if a matrix B is orthogonally diagonalizable, then it is symmetric by this way. And whatever we have done here, it is called the matrix A is orthogonal diagonalized. So, matrix A is orthogonally diagonalized or orthogonally diagonalized by this way. It means that the matrix P is orthogonal. So, this is the important theorem, that if a matrix is orthogonally diagonalizable, then definitely it should be symmetric, and if a matrix is symmetric matrix, then it definitely is orthogonally diagonalizable. So, this is a very important results we have. Now, so from here we have seen that if a matrix is symmetric, and if I am able to write P D P transpose, then I can also write this as eigenvalue decomposition of matrix A, that I am able to write the matrix A. So, A is a symmetric matrix, of course we know that. So, the matrix A, if I write in this form where P is orthogonal matrix, D is the diagonal matrix having the eigenvalues at the diagonal, like this one we have defined. This is my D, and if we are able to write in this form, then we say that the matrix A is a diagonal value decomposition of the matrix A. So, this we can do for a matrix which is symmetric matrix. We have also seen in the starting that if the algebraic multiplicity of the eigenvalue is same as the geometric multiplicity, then the matrix A is always diagonalizable. That we have already seen. Now, the thing is coming that what happen if any matrix A, that is n cross n, is not diagonalizable. So, this type of things happens when we have repeated eigenvalues. Repeated eigenvalues, because in the starting one we have shown that this eigenvalue is repeating 4 times, this eigenvalue is repeating 5 times, and this is n minus 9 times. So, whenever we have repeated eigenvalues, then it may diagonalizable or may not. So, that is one of the very important question about the matrix. So, and it happens when the repeated eigenvalue, because when we have a distinct eigenvalue, then the corresponding eigenvector will be linearly independent and that will be diagonalizable. So, now we want to see that what is going to happen now in this case. So, from here now we can say that if A is here, my A is symmetric, but here it is any arbitrary matrix. So, this is my any arbitrary matrix A. Now, if A is not diagonalizable, then we can define my matrix A, that is equal to P sum j P inverse. That we can do, where my J is called Jordan block matrix, or we also called Jordan-Canonical Form. So, this matrix J is the Jordan block, we call it. So, what is the J here? So, J is not a diagonal matrix, but J has the Jordan block of this type. Suppose, so this is we can do for here. So, let us see that suppose A is, I just take 3 cross 3 matrix, and suppose its eigenvalue is lambda, lambda, lambda. So, this is my repeated eigenvalue here, and so I can define at the algebraic multiplicity of lambda is 3, and let geometric multiplicity of lambda is 2. So, I just let us take the all the cases. So, let us take these cases on the next one. So, case 1. So, I am writing like this one. So, 3 eigenvalue, repeated eigenvalue. So, case 1, let algebraic multiplicity of lambda is 3 and geometric multiplicity of lambda is also 3. So, in this case my J will be D, it is just the diagonal matrix. So, in this case my J will be lambda 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 0 0 0 like this one. Case 2, let geometric multiplicity of lambda is 2. It means that here that the null space of A minus lambda I, the dimension is 2. It means we are able to find only 2 linearly independent vectors, eigenvectors. So, which implies that 2 linearly independent eigenvectors. Here 3 linearly independent eigenvectors. So, here I am able to find only 2 linearly independent eigenvectors. So, in this case I can write my Jacobian. So, I have lambda lambda lambda. So, it will be 3. Now, I have only 2 linearly independent eigenvectors. So, in that case my Jordan block matrix will be of this type, or my J will be lambda of this type. So, this is my Jordan block or the Jordan matrix, and this is one of the block. So, this is I just write one of the block, this one. So, this is corresponding to one eigenvector, and this is corresponding to one eigenvector. So, it is just the diagonal elements, no problem. Here also one Jordan block. So, this is one of the Jordan block corresponding to one eigenvector, another vector eigenvector is coming from here. So, this is the another Jordan block. So, one Jordan block means corresponding to one eigenvalue. So, this is the form we can have in this case, and now I will take the case 3. Geometric multiplicity of lambda is suppose 1. So, let geometric multiplicity of lambda is equal to 1. So, in this case we have only one linearly independent eigenvector. So, in that case I will get my matrix as lambda lambda lambda, it is 1, writing just 1 above the lambda and 1 here, 0 0 0. So, it is the type of upper triangular matrix, and this is my Jordan block and corresponding to one eigenvector. So, this is my Jordan form of the given matrix. So, based on this one I can write that my matrix A P is equal to P J, where P is made up of the vectors x1, x2, x3 in this case. Now, you see that in this case if I take the case 1, then this x1, x2, x3 will be linearly independent, no problem. If you take the case 2, in this case only I have able to get only 2 linearly independent eigenvectors. So, suppose this is the eigenvectors, this and this, and the x3 I will find from the from a method. So, in this case I can say that when matrix A is not diagonalizable, then I have a P on this form, and then x1, x2, x3 are called generalized eigenvectors. So, these are called the generalized eigenvectors. So, I will see that which one is generalized eigenvector and which one is not the generalized vector. So, I just write the definition first. So, just stop here this one, and we will write down the generalized definition of generalized eigenvector. So, in this case, so let us write down. Now, suppose I have a matrix A that is n cross n, and this is not diagonalizable. Then in that case, I want to find, then suppose I have a x. So, x, suppose x, then suppose A x is equal to lambda x. Is not diagonalizable, then a vector x is called a generalized eigenvector of matrix A of order m if order m associated with eigenvalue lambda if A minus lambda I power m x is 0 and A minus lambda I power m minus 1 x is not equal to 0. So, then only I will say that this vector x is a generalized eigenvector, and this we find when the matrices are not diagonalizable. So, now we can see that how we can define this one. So, now from here I will tell you that how we can find the Jordan form of the given matrix. So, I will just take the example. Let us take one example. Suppose I have a matrix A, and that is matrix, I just take 3 cross 3 matrix. So, this matrix, suppose I take this matrix, and this matrix having repeated eigen values lambda, 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 all the 3 eigenvalues are repeating. Then now and let the Jordan form of A is this one. Suppose it is this one, lambda, 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 1 0 1 0 0 0. So, this is my Jordan form of A is given to us. It means only one linearly independent eigenvector. Now, what I am going to do is that now from here suppose I get my matrix P. So, P is made up of suppose this eigenvector x1, x2, x3. Of course, it is a generalized eigenvector. So, let us I write like this one, and from here I get my matrix A P is equal to P j. So, I can write from here that this is my A and this is suppose x1, x2, x3, all the eigenvector written as a column vector, and this I can write as x1, x2, x3, and this j I am writing lambda 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 1 1 0. So, this is given to me because I have taken that suppose my matrix is A and having the repeated eigenvalue, and let us see Jordan form is this form way or the Jordan matrix. I can write the Jordan matrix here. I can see from here that A x1 now can be written as, I am just taking the first column multiplied by A. Again here also I am writing because A is 3 cross 3, it will be 3 cross 3. So, it is 3 cross 3 and this is also 3 cross 3. Now, A x1 I can write as multiplying this column. So, that gives me lambda x1. Now, from here I can say that x1 is an eigenvector of A. This is eigenvector of A corresponding to lambda eigenvalue. Now, I can write A x2 here multiplying the second column, and here also I am multiplying this second column with this matrix. So, it will give you x1 plus lambda x2, and from here I can write that A minus lambda I x2 is equal to x1. Now, this is we are able to write. Now, what I do is that I will multiply by lambda I both side. So, it will get lambda square x2 A minus lambda I x1. I just multiply with this matrix, and A minus lambda I x, this I can write from here that A minus lambda I x1 is equal to 0. So, from here I can get this value 0. So, from here I can write that A minus lambda I square x2 is 0 and A minus lambda I power 1 x2 is not 0, that we have already seen. So, from here I can say that x2 is a generalized eigenvector of order 2 associated with lambda. So, this is we are able to write. So, I can write this one as maybe 1, 2, and then this is from here I can write that is 3. Now, I am taking the third column. So, from third column I can write now A x3. So, if you take A x3 now multiplying by this way, so I will get my x2 plus lambda x3, And now, so maybe I can just instead of giving this numbers, maybe I can write here first part, second part, step. So, I can write steps, first step, second step, and then I can write third step. So, third step is this one. Now, from here you will see that I can write a minus lambda I x3 is equal to x2. Now, so from here you will see that a minus lambda I x2 is equal to x3. A minus lambda I just multiply by both side, and I will get a minus lambda I x2, because I am just multiplying by a minus lambda I on the both side. Now, a minus lambda I x2 is not 0. So, again I will write this one. So, also I will write a minus lambda I cube, multiplying both side by this one. So, I can write a minus lambda I square x2, and now a minus lambda I square x2 is 0. So, this gives me 0. So, from here I can say that a minus lambda I cube x3 is 0 and a minus lambda I square x3. So, that is already we have seen the square, this is not 0. So, I can say that x3 is a generalized eigenvector of order 3. x2 was the order 2, now it is order 3 associated with lambda. So, this way we are able to find x1, x2 and x3, and then I can write my P will be x1, x2, x3, and then based on this one I can define my matrix A, that will be P J P inverse. So, in this case the thing is that the P is invertible, but P is not the orthogonal matrix. So, it means that I can write for any matrix, I can write in this form whether it is diagonalizable or not, but we always can write the Jordan form of a given matrix. So, this way we can say that for any matrix A, we can write its Jordan form, and this is my Jordan form of the given matrix A. So, it means that I start with a matrix and I showed that if it is a diagonalizable it is okay, but if it is not diagonalizable then what we can do. Then we have seen that the things become simpler when the matrix P becomes the diagonal matrix or orthogonal matrix, and that is only possible when we have the matrix A is a symmetric matrix. So, if a matrix is symmetric, then we know that it is orthogonally diagonalizable, and with that one we are able to find this PT instead of P inverse. So, that is the one of the benefit. And then we have also seen here that if the matrix is not diagonalizable, then at least we can write its Jordan form, and this is the way we have shown that how we can write the different type of Jordan forms for depending upon the geometric multiplicity of the eigenvalues. And this is the way, this is the procedure that we can find out the generalized eigenvector for the corresponding eigenvalue lambda. So, maybe in the next lecture we will discuss some example and let you know that how we can define the generalized eigenvector for a given matrix. So, we will stop here. So, in the lecture today we have discussed about that which type of matrices are diagonalizable, and when the eigenvalues are repeating, then we know that matrix may or may not be diagonalizable. And then we have defined the another form that is called the Jordan form, and we have shown that any matrix A can be written in the form of a Jordan blocks. And so, in the next lecture we will continue with this one and we will discuss some example based on that. So, I hope that you have enjoyed this one. Thanks for watching. Thanks very much.